right, are we good with the camera? Okay, so it's a pleasure to welcome Max Raginsky, who's going to talk about, from UIUC, who's going to talk about compositional properties of statistical procedures. Looking forward to that.
Thanks, Moritz, and thanks to the organizers for inviting me and for some inexplicable reason asking me to make everybody suffer for an hour. So I'm going to talk about a very classical topic. Decision procedures, statistical decision procedures. And this is, essentially what everybody in statistics and machine learning is doing. You take data, which are generated by some random mechanism, and you map it to a decision. In machine learning, a decision is typically a function that allows you to make predictions on fresh samples from the same mechanism. In classical statistics, a decision is something about the supposed parameter of the population that the data came from. Right? But either way, it's a statistical decision procedure. It's a function from data to some action. And these days, we've heard many talks about adaptive composition, when essentially you have a sequential process where, so from now on, I'm going to use S to denote data. Sample, right? Typically, think about a tuple of IID samples from some unknown distribution, and that's your data. And a statistical decision procedure would take that, possibly randomized manner, generate some action W. And again, I'm paying dues to this modern viewpoint that neural networks are going to take over, and so the only decisions we make are about weights in the neural network, so whatever. Right? So this is a typical. Any statistical decision procedure looks like this. However, if you look in the guts of the statistical decision procedure, it actually consists of little incremental steps typically, because that's how we build things. This is how we engineer things, right? We take little building blocks and we compose them together. So really what might be happening is there could be some initial action W1, then you have another step that looks at the data, typically the same data, and a W1, and generates W2. And then, of course, if you have these multi-step decision procedures, the next thing might actually look at the data and at W1 and at W2 and generate W3, right? And you keep going. And at some point you stop. And let's say, depending on the context, you might just take the final point, like final, let's say W T, right? So this arrow is going from everything to it and from the data. Or you might actually take some subsequence of these because somehow you wanted to do this kind of multi-hypothesis testing or whatever. So you might take a subset of these. And then of course the question is, if we know, so this is how we think about this problem from a viewpoint of somebody who designs these things. Typically, the way you choose these building blocks is because they've been tested previously. You know their properties. Like each of these building blocks is something that in isolation you understand really well. But once you compose these things, knowing these local properties of the building blocks, what can you say about end-to-end performance of the statistical procedure, right? And all these recent works on what's called adaptive composition. This is exactly what these works call adaptive composition. Well, from viewpoint of, let's say, classical statistician, what are you adapting to here, right? Typically, adaptation is you have some unknown smoothness parameter. In a Sobolev ball, you don't know the constant, you don't know the radius, or something like that. You adapt to that automatically. From the viewpoint of classical statistics, there's no adaptation here. There is adaptation, however, because what you're doing is you're adapting to sort of past decisions in some sense, right? So, but the terminology is there, so let's call this adaptive composition. And when you describe this whole thing by a composition of what you would call essentially Markov kernels, right? Fancy speak. Because if this is a randomized procedure, if each of these is a randomized procedure, then essentially what you have is you have, I could call it something like this, if you want to be all fancy. It's a collection of probability measures on your action space, and this collection is indexed by the data, and this indexing is done in a measurable way, meaning that if I were to essentially ask a question like, okay, if I fix S, then this would be a probability distribution on your action space for any S. But on the other hand, if I fix A, so suppose A is a subset of my action space, and I look at this function. It's a function from data into probabilities. This function has to be measurable, right? So that at the very least you'd be able to take expectations with respect to the distribution of S. But then when you form this adaptive composition or composition, what you're doing is you're composing these Markov kernels in the following way. Now we have a distribution indexed by the same data set, but this distribution is over a tuple of these decisions, and it's a product, right? It's so essentially at each time t, what you do is you take your algorithm or procedure that you use at that time, and the other thing is that this also has dependence on all the previous decisions that you've made, or at least in principle may depend on all of them. And so this is, and so you're interested in the properties of this joint distribution indexed by the data set. Right, so in particular, one thing you might actually be interested in, at the very least, is if you marginalize out everything except for W capital T, right? So marginalize out everything except the last decision. What can we say about this? Right? So why do we care about this? Because let's suppose that, and now what I'm going to do is I'm going to just call this just W. So W is the last stage in my compositional structure. So one thing you might be interested in is something like bias, right? This is a question about generalization, right? So you typically would have some sort of a function. So again, we said that S is a tuple, typically IID from some distribution, and so you might have a function L of W and Z. So it's a loss of action W when the observation takes value Z, and then you, of course, might take the expectation. So if these Z's are IID according to some distribution mu, you might be interested in call it L of W or L mu of W. It's the expected value, right, of this with respect to a true data generating mechanism. But on the other hand, if you don't know this mu, which is typically the situation in machine learning and statistics, the best you can do is, well, one of the things you can do is compute the empirical loss, and this simply is denoted by L sub S, and it's simply, it's also an expectation. But with respect to the empirical distribution, that's denoted by this mu hat S dz, right? And mu hat S dz is simply the, it's the average of Dirac deltas sitting at the data points, right? And this is a kind of a classic thing, right? So there's no integral here, of course, because that's it's an expectation with respect to average of Dirac measures sitting in the samples, right? And then the question of quantifying bias or generalization, or however you might call it, is now if S and W are related through this statistical decision procedure, if I were to look at for fixed W, obviously I look at this L of W, and the expectation of this with respect to data is equal to precisely that, right? This is unbiased for any fixed W, or even for any random W that's independent of the data. However, if S and W are related through this mechanism, the procedure, then we know that in fact expected value of L of W minus LS of W is not 0. In fact, in general, it's going to be, if you're doing something like M estimation, this thing is going to be non-negative, because M estimators tend to be negatively biased. So we want to get estimates on this thing. And this is where the issue of stability comes in, right? And we've heard many talks about stability. Stability essentially means that if, in a sense, the decision W ultimately does not depend too much on any individual coordinate of the data set S, then we can expect that somehow you would get some sort of concentration out of this. And the way to think about this is to think classic concentration of measure. If you have a function of a bunch of independent random objects, and it doesn't depend too sensitively on any of them in particular, then this function will tend to be constant with high probability, right? That's the high dimensional concentration phenomenon. We expect something like that here, except of course the tricky thing here is that what we're looking at is a distribution valued function from a product space, right, into the space of measures on your action space. So how can we quantify stability? Well, one of the ways in which you could do this is you could say, all right, so let me look at this. Let me look at this distribution indexed by S, and imagine some other data set S prime. I mean, this is all well known. Some other S bar, data set S bar, where let's say I can compute the Hamming distance between S and S bar, and it's simply the number of coordinates in which the corresponding samples disagree. Right? And if this mapping is, let's say, so I suppose I can come up with some sort of a distance on distributions, and I could argue that this is Lipschitz. Right? Then you could say that C measures the sensitivity of my algorithm, decision procedure, to local modifications in the data, and from this I could presumably infer I could infer some sort of property of this bias. So this doesn't have to be a metric. You know, recent notions that we have seen in the literature replace this with some sort of information-theoretic measure of similarity or dissimilarity between distributions. For example, something like relative entropy. So you could look at Kolbeck-Leibler divergence. Let's say it's less than some epsilon. Well, so you know, C is typically something that's like 1 or 2 or whatever, and epsilon is typically small, right? It's just so this is called. And there are various names. I think the name in one of the more recent papers is max KL stability or something like this. Or you could look at differential privacy. Differential privacy is a way of essentially relating this to hypothesis tests. And differential privacy would mean something like this. If the Hamming distance between S and S prime is equal to S bar is equal to 1, then you could say something like this: for any measurable set A in your hypothesis space, you would have something like this: e to the delta E S bar A, e to the epsilon plus delta, right? So and actually this can be also related in terms of something called E gamma divergence, which I'm not going to go into, but you can relate this in terms of divergence, right? Okay, so all of these things somehow lead to statements about the expected value of this, and you expect that, you know, the smaller this epsilon, the smaller this is. Now the question is, okay, if you start composing these things, and you can say something about the properties, stability properties of each piece, how stable will the whole overall arrangement be? And this is a question that, you know, in fact, you know, if you abstract from the statistical nature of this is a question that they'll say engineers ask all the time. If I, you know, compose a bunch of building blocks and each of them doesn't mess things up too much, at what point does the whole arrangement come crashing down and I have to redesign things, right? And this is actually a very complicated question. You can think about, so you know, how can you quantify this? There are all these questions about, let's say, what's called adaptive composition. So let's suppose that each of these pieces is, let's say, epsilon stable in some sense. And I start accumulating this. How does this stability deteriorate? Well, in most cases, if you choose your things reasonably well, it deteriorates linearly, meaning that, you know, somehow if each piece is epsilon stable, you go through T rounds, the whole arrangement would be T epsilon stable. You could do better sometimes. And again, it's actually a very, very complicated question. Even if I know something about each of these pieces, what can I say about the whole arrangement? So since we've heard many, many talks about differential privacy and adaptive composition, stable medians, etc., I figure I won't be able to add anything to that work. What I want to talk about is a very, very actually, it's the fact that an algorithm or a procedure that we use all the time, or two procedures that we use all the time, are in fact compositional in nature, and we can begin to understand compositional properties by looking at these algorithms. And I'm talking about two things: MCMC and gradient descent, stochastic gradient descent in particular. And those are very, even though you don't think of them as compositions, you might even think about them as just gradient descent is like this primitive. It's something that's just there. You run it and it does things. But it's actually a composition, and moreover conditioned on the data S. Stochastic gradient descent is a Markov chain. With constant step size, it's actually a time homogeneous Markov chain. Markov chain Monte Carlo, by its very name, is also a Markov chain. So we might get somewhere with that. And now, even though my talk title has the word information theory in it, using information theory sometimes is not the most useful thing. For example, a lot of recent works started looking at, so let's forget about the compositional structure. For now, we have this stochastic mechanism that maps data to an action. You can look at the following things. You can look at, let's say, Shannon mutual information between S and W. And remember, since S is a tuple, if you can control this number, you could say something about the bias, right? So there's recent work by Russo and Zhou, and a follow-up work by my now former student, Aolin Xu. This will be presented at NIPS by Aolin. If the loss LWZ, so here Z comes from, Z is a distribution of an individual coordinate in your data set, and W here is an arbitrary deterministic hypothesis. If this is sigma sub Gaussian for each W, then the absolute value of the expected difference between, so this is the population risk or the expected risk of the hypothesis or the action returned by your procedure minus its empirical proxy. So this is a bound on the bias. This is smaller than square root of 2 sigma squared divided by n times the mutual information between the input and the output. So if this mutual information is small, in particular if it's constant, then then you're doing okay. But but in general, you might aim for something like it scales the number of samples, but scales at a moderate rate. So then you see that in fact you get bias is going to be on the order of square root epsilon. And this is actually a very weak guarantee, this mutual information. Right? Because, for example, things like differential privacy or max scale stability are generally much stronger requirements on the algorithm than mutual information. An earlier result that, let's see, so this was me, Sasha Rocklin, Matt Tsao, who's now he was an undergrad at the time. He's now a grad student at Stanford. Yihong Wu, who used to be at Illinois, now he's at Yale. And Aolin, this was presented in 2016. We considered a different measure of stability. We said, okay, let's consider the following. Let's look at the classic notion of stability that was proposed by Bousquet and Eliseev in the context of learning. They said, suppose I have a learning algorithm, right? So, or a decision procedure, right? And this is actually, remember that this S is a tuple. And suppose I told you, I hid, let's say I randomly picked an index from 1 to n, and I hid that example, a training example. I told you everything else, and I told you the hypothesis returned by the algorithm. How much would you know about that one example that I hid? So if, on average, this knowledge that you gain from even knowing most of the data set except one element and the hypothesis is not enough to pin down that example, well, then then you can expect stability. They phrased it in terms of expected losses or empirical losses, but you can phrase it also in terms of conditional mutual informations. So, so I would say that, suppose that, so this is what happens. I pick a coordinate uniformly at random, and I ask you a question. How much, knowing the hypothesis, and, so here I'm using notation z minus I to denote everything except for the ith coordinate, how much do you know about the ith coordinate? So this quantity is small. Then we say that this is stable in what's called erasure mutual information. This quantity on this sum is actually, this has a name. It's denoted by I minus W and S. And it's called erasure mutual information. It was introduced by Sergio Verdu and Sahi Weissman in a paper called Information Lost in Erasures. And in fact, you've seen a talk by Tom Steinke on Tuesday, where he talked about, on average, leave one out, KL stability or something like this. This is exactly this notion. So we showed that, in fact, under a slightly different condition. Here, in order not to make things too technical, you can assume that the loss function is bounded, and if the loss function is bounded by 0 and 1, then in that case, the bias is upper bounded by, well, constant. Let's see, so we have some sub-Gaussianistic. Some constant, depending on how you evaluate things, times epsilon. Right, so this is, this again is a, you can show that this erasure mutual information is smaller than mutual information minus something else. And so if mutual information, so it's a weaker criterion. If your mutual information is stable, then then you're going to be epsilon stable with respect to this erasure mutual information. Right. So you can, you can actually compute these things and show stability in this sense for a variety of algorithms. For example, one algorithm in which this can be verified very cleanly is what's called the Gibbs strategy. Right. The Gibbs strategy is when you pick a prior. So your distribution on the hypotheses given the data is proportional to some prior on the hypothesis space times e to the minus beta ls of w. So beta here is the temperature parameter, and then you can crank it up. And you can show that in fact all reasonable definitions of stability give you something like beta over n constants here. Right, so in that way, the erasure information is controlled, and in fact, this is if you know the differential privacy literature, this is the McSherry-Talware exponential mechanism. But of course, in statistical physics, this is the Gibbs distribution, and all sorts of large deviation principles are associated to it. So you can do things with that. Okay, but then we run into some problems. Because information theory is all good and well, why do we use information-theoretic concepts? Because we have chain rules, right? So, chain rules are important for quantifying composition. So chain rules are handy for quantifying composition. Right, so for example, we have this chain rule for mutual information. If I have, so remember that I have my data set S, and now suppose I actually do this adaptive composition. So I have T rounds. So by the chain rule for mutual information, this thing can be written like this: S, W, T, conditioned on everything that came before. So if you can control each of these terms and guarantee that that's smaller than epsilon, then you see where you have that linear degradation instability, right? The same thing goes for erasure mutual information. You can just apply chain rule to each term, and then collect terms, rearrange the summation, and get something like this. So these things that compose adaptively. That's why we like mutual information. However, here's an example where all this stuff fails spectacularly. It's just utterly useless. And the example is just estimating the mean when the data come from a density. Right? Suppose I have Z1 through Zn, and their IID according to some distribution mu, and then expectation of each of these things is equal to m. I want to estimate m. Right? So obviously the empirical mean is this, right? That's a good estimator. And it's clear that, okay, so let's suppose that my data are all bounded. So you actually, not only do you have, it's a good estimator in the sense of Chebyshev, it's a good estimator in the sense of Hefting, right? It concentrates nicely around the true mean, etc. Moreover, if the data are bounded, so if I change one of these points, the estimate will change by no more than 1 over n. So it's clearly stable in a very, very colloquial sense of the word. However, even the total variation distance, if I were to look at, so what is, if I were to look at the total variation distance, let's say, between the distribution of this empirical mean on one data set and another data set that differ in only one element. I mean, these are going to be mutually singular. You're basically going to get one, unless if at least one of these elements is if the training sets differ, if the Hamming distance between the two data sets is different, right? So and of course the mutual information is going to be large, and so you're not going to get anywhere with this. And yet deterministic estimators are a building block of things. For example, if I were to do, and this is just the simplest thing, but if I'm doing M estimation, I'm minimizing empirical mean of something over some parameter space. And again, it's a deterministic estimate, and typically those will be atomic measures, and any reasonable distance between atomic measures is going to max out. Mutual information is even worse, because if these things have a density, and I look at this transformation that maps Zn to their average, that's going to have infinite mutual information between the data and the decision. So then we thought, okay, let's think about this more geometrically. Let's think about in terms of distances in our actual hypothesis space. Wait, how much time do I have left?
You have a bunch of time. I think until 10:30, so 25 minutes.
Oh, 25. Okay, perfect. Okay, so that's actually a good point to introduce this whole transportation notion, right? So now let's think about the geometry of our space W. So suppose that W is, so these just running these markers into the ground. So each of these distributions, there we go, indexed by the data set, is an element of the space of distributions on my decision space. Now I'm going to assume that actually my decision space is a metric space with a metric row. And I'm also going to assume that in many cases, let's say the loss function L is Lipschitz with respect to that metric for each fixed z. Right, so assume z is less than or equal to L rho W prime. This is often the case. And so then naturally, I'm led to the following thing. If I can guarantee that somehow, okay, suppose that I fix two data sets, and S and S bar, Hamming distance between them is 1, and I generate WS from PS, and W's bar from PS bar. And then I look at Wasserstein distance between them. So I look at I'm going to call it D rho PS bar is going to be infimum over all joint distributions M that are distributions on a Cartesian product of W with itself of rho between W prime M dW prime. Right, so I'm looking at all joint distributions. Okay, so M. This is going to be, so the first marginal is going to be PS, and the second marginal is going to be PS bar. So I'm looking at all couplings, and I'm minimizing, this with respect to all such couplings. I'm looking at how much distance between these elements I can have. And I would say that the algorithm is Wasserstein stable if this thing is small whenever the Hamming distance between S and S bar is equal to 1. And that actually has a lot of interesting consequences. One important consequence is that Wasserstein distance has this dual characterization. Yeah, this is also kind of in the work with Aolin and Matt Tsao and Yi Hong and Sasha Rockman. Right, so Wasserstein distance d rho between two distributions P and Q is a supremum over all functions f that are one Lipschitz with respect to that metric rho, and it's expected difference between expected values. So f, I used capital F. Capital F, right? dp minus dq. So if you have an algorithm or a procedure which is Wasserstein stable, right? So if I could say that d rho ps bar is less than epsilon if the Hamming distance between S and S bars is 1, then essentially you see that the supremum over all S's of overall Z's rather, expected value of, let's say, what did I use for my loss function? L of WS Z conditioned on S minus L of WS bar and Z conditioned on S bar. This thing is going to be less than L times epsilon, and this is actually uniform stability. And that automatically tells you that the bias of this algorithm is also no more than L epsilon. Right, so that's already a geometric notion. It doesn't really ostensibly have anything to do with information theory, but we'll see later that information theory can be brought in if you can establish something called transportation cost inequality. The nice thing about this is that it satisfies triangle inequality, the Wasserstein distance. So if I can show, how would I show stability of an algorithm or a procedure? One way I could do it is to say that, oh, it's close to another algorithm, which is actually stable. Right. So then that would actually give me a criterion for deducing stability by, what happens a lot of times? A lot of times we have an algorithm which is good, in particular stable, but it's not particularly tractable. Or, it's less tractable than we'd want it to be. Case in point is something like gradient descent. Right, so let me demonstrate, and this is actually a very, very simple demonstration of this. Case in point is gradient descent. Which is meant to be, a stochastic gradient descent is meant to be a proxy for empirical risk minimization. Because empirical risk minimization involves, computing, minimizing a function, and it's a function is an average of individual losses on each training example, and a lot of times, even just doing full gradient descent is computationally intractable. Each step requires computing the gradient, which takes n operations, right? So we start with empirical risk minimization, right? So theta hat n, well, I don't want to call it theta. I mean, it's, in the classical mode, w hat n, deterministic thing, is a minimizer, let's say, unconstrained, whatever, of this empirical loss, right? So, and there's an interesting result due to, so there's a paper by Shalev Schwartz et al. Srebro Shamir, I think, that show that if L is, so on the strong convexity and Lipschitz, right? So here, of course, the problem is constrained, right? You can't have a function which is strongly convex in Lipschitz everywhere, but it can be on a compact set. So it means that W is constrained to be some compact set of in RD. ERM is actually big O of 1 over n stable in the usual sense. It essentially tells you that if I so let me indicate the data set here. You can actually show that the distance between, so again, Hamming distance is equal to 1. The distance between these minimizers squared is actually on the order of 1 over n. Right, so it is stable. So in fact, it is stable trivially in the Wasserstein sense, right? Because if these are two deterministic, two Dirac measures, the Wasserstein distance between two Dirac measures is simply the distance between their centers, right? Because that's the only way I can transport one onto the other. But it turns out that, but now, this is, how would you solve ERM? Typically intractable if n is large, so you would use stochastic gradient descent. Right, so stochastic gradient descent, what is it? It's actually stochastic approximation with respect to the empirical measure. So, one way to think about it, if you have a fixed data set, you sample with replacement. So you have this bag of examples, you shake it, reach in, and pull one, take the gradient in that direction. This is essentially the situation where usual stochastic approximation thing, where I want to minimize an expected value of something with respect to a parameter. And what I do is, instead of minimizing the expected value, I draw samples from that distribution, right, each time, and treat that as it's an unbiased estimate of the gradient, etc. Right, so stochastic gradient descent with sampling with replacement is simply stochastic approximation with respect to the empirical distribution of the samples. And then you can actually show that, so essentially here, stochastic gradient descent, it's Wt plus 1 is a projection onto my set W of Wt minus eta, and then you have gradient of L with respect to Wt, and then randomly selected It here is, these It are IID, I1, It. IID draws from uniform distribution on a set of indices. And then you can show, using more or less stochastic approximation theory, that the expected value of the square distance between Wt plus 1, and here let's put S here, again, to indicate dependence on the data set S. Right, so you can show that this minus that is actually, this is big O of 1 over t. Right, so, and that actually tells me that the Wasserstein distance with Euclidean norm, right? So, kind of just usual Euclidean norm between, let's say, so SGD t steps and PERM, right? This is actually O of 1 root t. And now I can actually say something like this. So, so I'm going to say P SGD t steps S, P SGD t steps on a different data set that differs in one example. Triangle inequality then tells me simply that this is less than that, plus the same thing for the other data set. S, E, R. Yeah, my board handwriting is notoriously bad, and students complain all the time. Plus, essentially, the distance between the ERM solutions, right? So W hat N S and W hat S bar. And this is 1 over n, and these two terms are 1 over square root t. So you get something like this is O of 1 over n plus 1 over square root t. In fact, I think you can actually remove the square here. Right. So this estimate, okay. So it's not the best you can do for stochastic gradient descent with strongly convex and Lipschitz objectives, but at least it tells you that this is actually a very sensible procedure. If you have an algorithm which is compositional, and this obviously is compositional, right? Because you take your data set and you start and in fact your initialization is maybe even independent of the data, and then you start computing in this Markovian manner, right? So W3 depends on W2 and S. W4 depends on W3 and S. It's a Markov. So conditioned on the data, it's a Markov chain. It's still a composition. It's just that you don't normally think about gradient descent as a compositional thing. It's a black box, but it really is a composition. And here what we're saying is that I can approximate it by another algorithm, which I know to be stable. In this case, just a vanilla ERM. Right? And then you see that in fact I can look at the progress that this makes towards optimizing t steps. In fact, these terms can, this 1 over root t can be improved, and there's some conditions. There's this whole work on importance sampling for SGD under some conditions that this 1 over t or 1 over root t can actually be made exponential in t. So you can get a statement about stability this way. Not particularly it's not particularly easy to do something like this when the assumption of strong convexity is removed. So in particular, so the best bound we have is in the paper by Moritz, Benrecht, and Yoram Singer, train faster, generalize better. I suspect that can be improved, simply because we have, even in the case of non-convex but sufficiently well-behaved functions, we have stochastic gradient descent is still a Markov chain, which should still have decent convergence properties. But I've been unable to do anything about that. But I can show one particular way in which one can handle, compositions of algorithms and say something about their Wasserstein stability using something called the Bruijn comparison theorem. I don't want to give the full background on this theorem. I just want to say state the following fact. Okay, so it's going to apply apply to an arbitrary adaptive composition. So we have, consider PS dw1 through dwt. It's a product of these individual steps. It's dwt given previous steps. And suppose the following. Well, no, not suppose, but define the following things. C, S, don't want to use S. S is data. TT prime is the supremum over all. Let's see. So here, let's see if here one case would be when t prime is greater than when t is greater than t prime. Supremum over all tuples w t, w bar t, such that wt is equal to w bar t except everywhere except t prime. So they may disagree in the index t prime. And then you would look at the Wasserstein distance with respect to a suitable metric. So you endow each space with a metric. So Wasserstein distance between the distribution on dw t given everything else. Okay, I'm messing this up horribly. And given wt minus 1 and ps dwt given w prime t minus 1. Like I said, my handwriting is awful. Divided by the metric between wt and t prime here. Right, so the idea is what we're doing is we're looking at the distance. So if I have two different paths by which I could have arrived by time t, I look at the difference between the distributions and scale it. Look at the contraction basically, and zero otherwise. And epsilon t would be the Wasserstein distance between P S, let's see here, dw t given everything, and ps bar dw t given everything. So here, C's measure when we feed the same data set, but possibly somehow ended up with different trajectories in the past. How would that affect the trajectory in the future, right? The path of the algorithm in the future. Epsilons are essentially stability steps of each stability estimates for each step. Then you can show that for any function on expectation of any function, Lipschitz function, on the last step of the algorithm, minus this, f of wt, is less than or equal to, it's a sum, t from 1 to capital T, of, so this function is Lipschitz, right? So for L Lipschitz f, Lipschitz constant, and then there's going to be a matrix D, I'm going to define it, T epsilon T, where what is D? What is this matrix D? D is it's the powers of this matrix C, CT, assuming of course that this series converges. This is called, this is a consequence of the so-called the Bruijn comparison theorem. And you can actually, so you can immediately show that, in fact, my previous estimate for SGD with strongly convex objectives is very loose. You can actually get something, stability does not even depend on t. It's just, scale is 1 over n. This is also the result in a paper by Moritz, Ben, and Yoram, but I just obtained it differently. I mean, despite my horrible handwriting, here the idea is that each step of the algorithm, each compositional step, the stability of that is influenced by two things: how stable each of the compositional steps by itself, right? So this is this quantity, right? Distance between. So at each stage, I'm looking at two different data sets, and I'm saying, okay, how if I change the data sets but the algorithms run the same way, how different are they? But this says, okay, well, the thing is that you could have, in fact, arrived at, by the time t, you could have, let's say with stochastic gradient descent. This is actually kind of similar to these ideas in the Train Faster, Generalize Better paper. The two data sets differ in one element. At some point, you're going to hit that element in which they differ, so the gradients are going to be different. At this point, the gradient updates are going to diverge from one another. They're going to drift apart. This quantifies that. So if we have an algorithm that somehow does not allow the iterates to drift too much, right? So these dependencies become weaker and weaker and weaker, and somehow each of the steps is stable, then we can have an overall stable algorithm. But unfortunately, I've only been able to prove that to use this non-trivially for the case of stochastic gradient descent with strongly convex and smooth objectives. And like I said, probably the importance sampling, the Kaczmarz method, could probably be analyzed and get the same conclusion. But this at least paves the way, and this is based, like I said, based on the Bruijn comparison theorem. It's not, I shouldn't even call it a theorem. It's a straightforward kind of just application of the Bruijn comparison theorem to this idea. But as far as I know, if we have local description of these compositional steps, the Bruijn comparison theorem is the best tool that we have, the best generic tool that we have for quantifying these things. Okay, how am I doing on time now?
I have like 5 minutes.
Okay, 5 minutes is fine. So now I just want to. Sorry.
Just the notation. So little d t t is the last row of this matrix, capital D?
Yes, that's the last row. Because I'm only, so in general though, if you could look at the function of all the w's, you would have to sum over all the rows and all the columns. But here, if I only care about the last iterate, then I use the last row. And so now I want to just I talked about these deterministic algorithms for quite a while. And by the way, I don't think I'll get to MCMC. But I want to actually explain a little bit of how this would work. And this is actually fairly simple in the case of SGD, if I have 5 minutes. In the case of SGD with strongly convex objectives. So what happens? What does your Markov kernel look like? It looks like this. If I were to be really fancy and write it out, at time t, given previous data, it's an average of Dirac deltas, and the Dirac deltas sit. Let's suppose so that's a projection of Wt minus eta times the gradient of the loss at the ith example, sitting at dWt. Well, right. So I'll put dot here, and right, because that's what you do. It corresponds to selecting a training point at random and then going in the direction of that gradient and then projecting. So you can actually. So how would you compute the the Wasserstein distance? One thing you could do is just simplest Wasserstein distances, and this is in fact the. So we talk about couplings. This is the coupling that Moritz and Ben and Yoram used in their paper. The word coupling didn't appear in that, but it really is that. What you do is you start with two different data sets, but these ITs, the indices that select the training examples are the same. So you couple two Markov chains through the same noise. It's called synchronous coupling. And in that case, you can actually see that if WST minus W S bar T, right? If I know this, right? So the distance between these, Euclidean distance, by the non-expansiveness of projections is upper bounded. Well, square is easier. Is equal to exactly the distance between T minus 1 S minus twice, let's see, eta, and then you have this, that, inner product with the difference of gradients, W S T minus 1 Z I, right? They couple to the same, noise, right? So minus the gradient here, minus the gradient. E S R I W, right? Plus the difference of gradients, eta squared, right? Sorry, my handwriting, my board handwriting, in fact, just gets worse with W prime S, T minus 1, Zi. And then you can actually see that because of the strong convexity and things like that, this can be upper bounded by 1 minus, there's going to be 2 eta, this is going to be the strong convexity constant plus eta squared, m squared, if the gradient is Lipschitz, times this, right? So Ws T minus 1 minus Ws bar T minus 1. So you can see that by taking eta small enough, you can make sure that this is a contraction. So these terms here are all less than 1. So that matrix D, when I take powers, essentially I'm summing a convergent geometric series, and I end up with exactly the estimate. And this term here, this epsilon t, is actually 1 over n, or big O of 1 over n, because this corresponds to the case when I have two different data sets with different one examples. So for the most part, unless I hit that one example, I'm going to have exact coincidence. But that example is hit with probability 1 over n. So you get 1 over n difference there. So
yeah. So you're now out of time.
And now I'm out of time. But the point is that, okay, so I didn't get to the MCMC, of course, but I think that this idea based on kind of geometric or Wasserstein distances is also a fruitful way for analyzing stability of compositions of statistical decision procedures. So hopefully in some later point in time, I'll tell you more about this and with more refined results. Thanks for suffering through this.
So, I'm not sure if SGD will work in the non-smooth case. I guess not. But is there any hope for analyzing first-order methods in the non-smooth setting?
Not that. Oh, so some other first-order, like maybe with more than Markov updates or something like that, with momentum. Yeah, I mean, so in the case of Markov updates, it's just this matrix C is it has a single, it's zeros everywhere except right below the main diagonal. So you could have banded matrices, and then you just as long as you can arrange for for this D to be as long as the spectral radius of C is less than 1, you're okay. But of course for each specific algorithm you have to kind of. I mean, one hope I have is to analyze the case where your function is strongly convex outside some ball, and has manageable behavior inside that ball. So perhaps one could do something with that, but probably some sort of momentum-based methods.
Right, let's take more questions into the break. We now have a 25-minute break, and then big news next.